Okay, I guess we can get started. Welcome back. I'm glad you two made it in today, and welcome to the others that will probably see this video later. For today's class, we're going to be running through sections 8.5, 8.6, on solving square root, cube root equations, and so on, radical equations, and then taking a brief look into the complex number system. This section here is very short, so we're probably going to be spending most of the time in section 8.6. Well, that's the major roundup for the announcements. The big one is we have exam 3 that's going to be in 2 weeks from today. So this one will be right before we go on to the Thanksgiving break. So that'd be kind of nice to have it squared away and not looming in the back of our minds while we're on vacation for a week. But because this one is in 2 weeks, that means when I get to Friday of this week, so on November 7, the first thing I'm going to do on Friday morning is going to be filling out the exam 3 information and writing in the sample exams, just like we did for both exams 1 and exam 2. Well, any questions at the moment, folks, before we jump back to section 8.5? Well, thanks for asking about that, Tracy. So problem from homework, and this one is simplify. Some of it kind of got messed up in the text, but let me know if I can get this translated just right. So I think I know what you're saying, n power 3, p power 9. But then the 147 is kind of messing me up at the moment. So let me see if I can get this in just as how I might interpret it. Oh, I see what happened then. That was a copy paste error. So it might have been simplify. And we've got square root 348 m cubed p power 9. And I'm assuming maybe it was a simplify that goes like this. Let me know if this is on the right track. Almost looks like it's 2 square roots. Then another square root with 147 m squared p power 11. Does that look about right as written? Oh, gotcha. So divided by 147. In a way, that's kind of nice because that means that 348 over 147 might reduce a little bit more for us, making it kind of a nicer problem in a way. So over square root 147 m squared p power 11. I think this is a fantastic problem to start off the class. It's similar to the ones we were doing right up here, so a great warm up to get us started. Okay, so let's try this one out. Thanks again for suggesting this, Tracy. I'm sure the others, when they take a look into this video, will appreciate taking a look into this one as well. And first thing I would probably deal with in trying to simplify this down is write this under 1 overall square root. So we're looking into the square root of 348 m cubed p power 9 over 147 m squared p power 11. And the thing that's tricky and interesting about this is the more abstract part, the variables m and p, are not the hardest part about this. I would say to me, the hardest part about this is the integer portions, 348 divided by 147. First thing I'd probably try to do is see how can they reduce? The numerator is even, but the denominator is odd, so we can't divide by 2. I wonder, could we divide by 3? Let's see. 147, I should test the numerator first just to keep it in order. 348 divided by 3, that goes in nicely. I think the denominator should be divisible by 3. Let's test it out. 147 divided by 3 goes in 49. And that gives us something to work with. The 49 is nice because that's a perfect square. So let's start off by just reducing the fraction itself. Let me save this result over here for the moment. So we've got one overall square root that goes like this. Division by 3, I already forgot what the numerator was, gives us 116. Division by 3 here gives us a 49. So it's now 116 divided by 49. Next thing we can do is reduce m squared into m cubed. We can have just m when we do that reduction. M cubed divided by m squared comes out as just an m in the denominator. Slightly differently for base p, when it's p power 9 over p power 11, this reduces as p power 1 over p power 2. So we'll have p squared in the denominator. Still, that 116 is kind of mysterious to deal with. So at this point, I'd probably just start factoring down this portion. To take the square root or simplify the square root of 116, a factor tree could help us out. So first we can divide 2 into 116 58 times. Then 2 will go into there, let's see, 29, or goes into, yeah, I think that's about 29 times. At this stage, 29 is a prime number, so this looks like as far as it will reduce. Let's double check that arithmetic. 2 times 2 times 29. Yeah, that gives us back the 116. So best way to write 116 is as 2 squared times 29. So I'll substitute that information in where we see the 116. And now here's the next line. We brought it together just so we can simplify the radicand down to this portion. But now we're going to split up the square roots, kind of like how the problem started. So it's 2 squared times 29, m in the numerator. And in the denominator, we're taking the square root of, you could leave it as a 49 if you prefer, or write it in as a 7 squared. Let's do a 7 squared, so it looks kind of similar to the numerator with a 2 squared times p squared. Now, the thing color-coded in green is the perfect squares, the thing we can take the square root of. So that's the entire denominator, 7 squared and p squared. We can square root 2 squared here. But 29m, there's nothing we can do with. These are both to powers 1. 29 being prime, can't factor further. And so here's the overall solution to this one. Square root of the denominator comes in as just 7 times p. Taking the square root of the numerator is going to give us just a 2 to come out, leaving behind square root 29m. So that would be its simplest form once we get it down to this stage. Definitely a pretty tough one, especially with the size of the numbers there. But any questions at all getting through this one? Yeah, absolutely. Thanks for suggesting that again. That's always a great way to start class out, I'd say. Well, we're going to work through these notes in full. We just have example 3 at the very bottom to get through. But any other questions at the moment at all before we run through the rest of the notes? Okay, and again, I'll always take questions at the very start of class. So anything that just seems nasty in the Newton homework system or otherwise, don't hesitate to bring. I always think that's a great way to start off class. So here's how the notes started in this section. And it's a pretty complicated section because, well, another reminder is section 8.4, operation with radical expressions, involved adding, subtracting the radicals, then multiplying the radicals. And then we left in the entirety of section 8.5 the concept of division of radicals. It's because the concept of having a radical simplified involves these two tricky parts, parts 2 and parts 3. Anytime there's a fraction as the radicand, the thing inside the root, when that occurs, we say the thing is not simplified. And anytime there's a radical in the denominator, whether it's a square root, cube root, or otherwise, say like in this example, we say it's not simplified as well. That's what happened in example 1. That's what happened in the problem we took a look at right here as well. There's a square root symbol, a radical expression in the denominator. In these examples here, whether it's a fraction or just a square root in the denominator, the concept was split them up as necessary, like in part A, or if it's already been split up, do this little concept. If you multiply by the square root of 3 over the square root of 3 to match that square root of 3, when these two multiply, you get a 3 back, and now it's simplified to a root 3. Only because it doesn't have a square root in the denominator, this is now up in the numerator. So we looked at various ways that goes along, and that takes us all the way down to example 3. With a major trick, the concept for solving each one of these is to multiply by the conjugate to simplify the expression. Well, one thing we can think about is we can't multiply by root 2 over root 2 on this one like the others, because if you multiply by root 2, they'll multiply here, giving you a 2, but also distributes to the 3, giving us a 3 root 2. We're back to the same problem. We have a square root in the denominator. So here's the idea we're going to connect together. If you have 3 plus root 2, its conjugate, so this thing we were multiplying by, or mentioning we need to multiply by, its conjugate is 3 minus square root of 2. So it's almost the same thing, but the only thing we change is whatever the sign is in the middle, we take the opposite sign. So if it was a 3 minus root 2, we'd have written 3 minus root 2 here, and the conjugate would have been a 3 plus root 2. So this thing is somehow, some way, going to wipe out the square root symbol from the denominator completely. It's not going to end up in one term or the other. And here's how it goes. We have 7 over 3 plus the square root of 2. Multiplying by the conjugate means we'll take 3 minus root 2 in the denominator, 3 minus root 2 in the numerator. And so now this whole thing is just a fancy multiply by 1. So we're not damaging the equality here, it's still valid. We have to associate in this way, multiply through the numerator. In the numerator, I'm going to leave the 7 in a factored form, so I'll just write it as 7 times 3 minus the square root of 2. But in the denominator, we do want to FOIL this out entirely, but there's always a huge shortcut if you have a conjugate pair like this one and its conjugate to 3 minus root 2. The middle terms are just going to cancel out completely, and it's through this formula. Oops, let me fix the color coding over here first. If you take anything of the form a plus b times a minus b, whether there's square roots inside or not, this becomes the difference of squares formula. FOILing has the middle terms canceling, and you're left with a squared minus b squared. So if you square this, you'd have gotten a 9. If you square root 2, you get a positive 2 out, and there's just going to be a minus sign in the middle. If we FOILed it out in full, this is what it would look like. 3 times 3 gives us the 9. That's the a squared portion right here. Then you take 3 times negative root 2, so that's just going to be a minus 3 root 2. Next, take root 2 times 3. That's going to be a positive 3 root 2. And finally, root 2 times root 2, this is the concept from the section 8.4. A square root times itself just gives you back the radicand. So root 2 times root 2 is just 2 itself. So this becomes a minus 2. But minus 2 is just square root of 2 squared. In other words, root 2 times root 2 equals root 2 can be just thought of as root 2 squared, but either way you write it, you get a 2 out. The root 2 squared is like the b squared that we see over here. And just like we predicted, middle terms completely cancel out from this. So it's kind of a nice process. If you multiply by the conjugate, you just square that first term, 3 there, to get the 9. You do put a minus in the middle, square this term, but the square of the root 2 just gives you a positive 2 with a minus in the middle. So we've done the essential step. The square root expression is considered simplified in the sense that it doesn't have a square root in the denominator. We still have to simplify it in full. We have to combine the like terms, 9 minus 2. So the numerator is 7 minus 3 root 2. The denominator is just a 7. Now we get a bonus cancellation. The 7s here cancel off. And this is just a 3 minus root 2 in its entirety. And that seems really strange, right? 7 divided by 3 plus root 2 is the same exact quantity as 3 minus the root of 2. It's deceptive because they look totally different, but that's why we simplify in this kind of way. We're just standardizing our answers, so we never get tripped up by competing looking versions of the same exact quantity. Well, any last questions at all, folks? Double checking or getting through this full process? Okay, and just one more concept, because seeing is believing on this. You do have a pretty good check whenever you do this kind of problem. It looks like this. Put the original thing into the calculator. 7 divided by 3 plus square root 2 comes out as about 1.585. Then our simplified version, we like this answer better, but if we want to see what the decimal answer is, in the calculator, go 3 minus square root 2, and it's the same exact decimal expansion. And there's a possibility that we made some weird mistake where it differs in the next decimal values that were shown, but that's highly unlikely at this point. If you're getting the same expansions from here to here on both versions, you have a gargantuan amount of numerical evidence that we did it correctly from start to finish. It's kind of nice because 3 minus root 2 really looks like it's a simplified version versus this one, which had a fraction. So the last part of the notes is just practicing this technique in a couple of different ways. So let's try it out again with 6 divided by 4 minus square root 3. We start off just like before. Let me recopy it so we know what the problem was we started with. 6 over 4 minus root 3. Then we multiply by the number 1, but just written in a slightly different form. The conjugate this time is different. The conjugate involves a plus. So we go 4 plus root 3. 4 plus root 3. Let's write this into our notes because it's still a pretty new concept. The conjugate of the thing we started with, 4 minus root 3, is 4 plus root 3. So the only thing we had to be sure of was flipping the sign, whatever it might be. So we flipped from negative to positive, just like from over here, we flipped from positive over to negative. Then we have to FOIL all this out, so let's insert our parentheses. And even though there's a shortcut where the terms in the middle do cancel each and every time, there's no harm in FOILing it out if you want to be just extra careful. Let's maybe do the shortcut on the next problem. For this one, because leaving 7 in the factored form turned out to be helpful, it allowed us to reduce, let's copy that principle and write this as just 6 times 4 plus root 3. In a certain sense, that's a nice format. It's nice and factored. The greatest common factor has been factored out. And so there's really no call to distribute 6 into the group. If you're doing these kinds of problems, you can always leave your answer in its factored form. Now take the 4, distribute it into both of these terms. We'll get 16 plus 4 root 3. Do the same with this negative root 3, distribute it into these two terms. We'll get minus 4 root 3. And then negative, because it's a negative times a negative, but root 3 times root 3 comes out as itself, just like root 2 times root 2 is just 2. That gives us the nice cancellations we were expecting in the middle. And then this problem just becomes 6 times 4 plus root 3 over 16 minus 3 is 13. At this stage, this is a totally fine stopping point. If you multiply 6 into the group, that's completely fine as well. The homework system would take either version of those answers. Well, this one didn't simplify as nice as the last one. The last one went from a fraction to just this expression, but it's considered more simplified on this problem just because there's no square root in the denominator. So in a very real sense, we've standardized the numerical value from what we had over here. Well, any last questions, folks, before we try it one more time? Okay, let's try out to one more. Really, the only way to make it feel more abstract, slightly more difficult, is to throw a variable in, like we have over here, square root of x. And this time there's also two square roots, so it feels like a more built-up problem. But really, it's the same concept. If you multiply by the conjugate, you clean up the denominator by removing the square roots. So let's try this out one more time. 4 over square root of x plus square root of 10. The conjugate is going to have a minus this time, flipping the sign from here. So it'll be root x minus root 10 in both numerator and denominator. Then we expand out the expressions. One thing that we noted is each time we do this, really all we're doing is squaring the 4 to get the 16, squaring the root 3 to get the 3 here, and making sure there's a negative sign in the middle. In other words, it's just this formula that you're using every single time you multiply by the conjugate. So let's take that shortcut this one time just to see visually what does it actually look like on paper. If we use the shortcut, you'd be squaring root x. So you just get an x out. You make sure minus is in the middle. We're matching this minus sign right here. Then you square the root of 10. Root 10 squared just gives you a positive 10. And then it's done. Multiplying this by its conjugate, that's all you would get as a result. Similarly, with all the last problems we looked at in example 3, the numerator is going to be 4 times root x minus root 10. So the numerator definitely got a lot more complicated. The whole thing looks more complicated, but at least there's no square roots in the denominator. So this is the simplified version on the right. And the problem really is that quick at that point. There's nothing further to show right at that step. Well, we did it, folks. That's the end of section 8.5. Any last questions at all, finalizing this section? Okay, well, we've done a lot of stuff with this square root so far over the last class meetings. This is going to culminate in the very next section, 8.6. We're going to take the ideas that we've been working on, particularly the rational exponents, and solve equations involving radicals, square roots, cube roots, and so on. So here's the next really big section. There's still one more section, 8.8, in chapter 8, but that one, like we mentioned, is just a pretty short piece of work dealing with complex numbers. So here's the larger section, equation solving. Here we're looking at the concept of dealing with extraneous solutions once again. So just for a refresher and a reminder, we have dealt with extraneous solutions before. An extraneous solution comes up whenever we're taking the correct algebraic steps to solve an equation, like a square root equation, but the number we get when we take the normal steps in solving it is not a solution to the original equation. This came up all the way back in chapter 7 when we were solving rational equations. So let's take a preview of that just as a warm-up of the extraneous solution concept. Rational equations were also pretty tricky. The things that cause problems were the so-called excluded values. They were values that makes the denominator go to 0. Let's go to one that had some particularly interesting issues. That'd be part B of example 2. Here, the denominator could have never been a positive 2. So we said the excluded value is v cannot equal 2. But when we went to solve this whole equation, our first step was to use the least common denominator to clear out all denominators. we got this equation, which reduced down to the statement 6v minus 10 equals v. Soon we had 5v equals 10, and we came up with v equals 2. We didn't make any mistakes in the algebra, but it just so happened that any way you try to solve this equation, if you get a value v equals 2, it's not a solution whatsoever because 2 doesn't check in this equation. So this was a one that had no solutions whatsoever. It got even weirder because this is one where when we took the same kind of steps, we found two solutions, but only one worked, x equals 4. If you try to plug -6, you had a problem right here. So those same kind of ideas come back in the current section. Any questions at the moment with these rational equations and those excluded values? Okay, here's where it becomes relatively relevant again. When we're solving radical equations, that's always kind of a strange word, but what we mean by a radical equation is there's a root somewhere in the equation. It's either a square root, a cube root, a fifth root, maybe an eighth root, and so on. These have extraneous solutions, but only when the index itself is even. So the square roots, we have to check to see if we have an extraneous solution on. Same with part B, there's another square root. But on the cube root, if the index is odd, there's no problem with these. The solution you find here is guaranteed to be the real solution. They're never an extraneous one. So we'll be careful every time we have an even index. We'll make a big deal out of it, and we'll check our answers to see if we're excluded anything. And just like with that section on rational equations, a lot of different things can happen. Sometimes there's no solutions, sometimes only one value is a solution, and sometimes everything solves the equation, just depends on the problem. So even index is the major thing we're looking for. And on part A, we have a square root, so there's an even index. Square root gives an even index of 2. So here's how we solve this equation. It's kind of nicer than what we did in section 7.4, the rational equations. That one was a lot of algebra. A lot of people had concepts that seems like a pretty long problem, but these ones are typically a lot shorter. We start off by taking the square root of 7x plus 1, give it a little bit of space, it's set equal to 6, and the first thing we do right away is just raise both sides to the power of 2. That's because the index right here is 2, and we're trying to match up whatever power we take over here with the index of 2. This causes a particularly nice cancellation. The square root, the entire thing cancels off, leaving 7x plus 1. The right-hand side becomes 6 times 6 for 36, and we've eliminated the root from the equation entirely. Now it's just an ordinary linear equation. The reason that works out, this little trick where the root canceled, is if you have a base A for anything that you're taking the square root of, but then you squared that, our section on rational exponents tells us that this square root right here, because it has an index of 2, is really just a to the power of 1/2. But then our work on exponents tells us in this configuration, the exponents 2 multiplies the 1/2. These exponents right here just multiply, so this becomes a to the power of 1/2 times 2, but that's just a power 1, resulting in a. 7x plus 1 is the a in this problem, and so raising the square root to the power of 2 just completely nullifies, cancels off that square root. But it also means we might get an extraneous solution, so we'll have to watch out for that. So this is the whole big idea of the section. If this was a cube root, we'd have just raised this to a power 3, and so on. Now, solving for this, we'll just subtract 1 from both sides. 7x is 35. Divide by 7, and x is 5. But because we had an even index in this problem, we can't celebrate early. we have to check our solution. So let's do that check right here. If we set x equals 5, that means we'll plug 5 here and get root 7 times 5 plus 1 equals 6. Then let's just simplify to see if this is a valid equation. Inside the square root by order of operations, this is now 35 plus 1, supposed to be equal to 6. The square root radicand simplifies to root 36 equals 6. At this point, I would trust that result. The square root of 36 is 6, because 6 squared is 36. And so x equals 5 is the answer to this one. And I'll box off the answers whenever we do a check, just to emphasize this is the only thing that's correct for the solution. Well, that's one down. We have quite a bit more to go through in this section. But this is the key takeaway. Whatever your index is, raise it to that power, and you have a cancellation. Let's use a different color coding to really emphasize that. Let's use green right here. The power 2 here, and this is where we get the cancellation. Well, let's try this out in a slightly different kind of problem. This one's a little bit more tough because if you were to square this problem right away, the square root right here by the red dot does not eliminate. You'd be FOILing out 4 root x minus x to the power of 2. That just spreads out your square roots into various places. So the way we'd start off this one is isolate the square root term. So if we can get 4 root x all alone, this becomes a much easier problem. We can cancel that root a lot nicer. That just boils down to add x to both sides. So the equation becomes 4 root x equals x minus 5. Then once we get to this step, because we're dealing with the square root, we raise both sides to the power 2 this time. Just like last time as well. So the left-hand side is now to power 2, as is the right-hand side. We do have to be a little bit careful because this is an exponent law already right here. The exponent law is that a times b to power m is a to the power of m times b to the power of m. So when we go to square this, first we're squaring 4. Then we're squaring the square root. But that's where our cancellation comes into play. The index inside, even though we don't always write it in, is an index of 2. Raised to a power 2 cancels in this way. So it's equal to x minus 5 squared. So x minus 5 times x minus 5. That means when we square on this step, we are just getting a 16. That's the 4 squared. Square root of x squared is just giving us an x altogether. And now there's no square root whatsoever left over in this problem. We just have to FOIL out x minus 5 times x minus 5. Distributing x, we have x squared minus 5x. Distributing in the negative 5, we get negative 5x plus 25. And I'm thinking we're going to need more space on this one. At this stage, we're just solving now a quadratic equation. So this turned into a chapter 8 problem from the start into a chapter 6 problem, solving the quadratic equation. So let's combine our like terms just to simplify it further. 16x is x squared minus 10x plus 25. Subtract 16x from both sides, and 0 equals x squared minus 26x plus 25. We now want to use a zero product property, which means factor that polynomial that we see here. So this one factors in a nice way. We can go x and x. That positive sign here means both of the inner sides are the same. And that negative sign says they're both minus signs. And to get a 26, we can just go a 25 and a 1. These will multiply out to a positive 25, add up to the negative 26. And so now at the next stage, the zero product property tells us the only way those two groups multiplied for a 0 is if x minus 25 is 0 or x minus 1 is 0. Then we solve both equations. X is either 25 or x is 21, excuse me, positive 1. So these are both solutions. They could both potentially solve the original equation, or maybe one does and not the other, or maybe none of them solve this equation. It could be like in our section 7.4 where this one had just no solutions. So because the index is even, it's a square root, we have to do that check. So here's our check for an even index. We have to look at both solutions, and we plug them into the very original equation all the way up at the top. Let's just go in line, starting in order. When x is 25, we'll plug it up in here and get 4 root 25 minus 25 must be a negative 5 for this to be a real solution. Then simplify here. Square root of 25 is just a 5. So this is 4 times 5 minus 25 equals a negative 5. At this stage, I'm convinced this is just 20 minus 25 equals negative 5. You only have to do as many steps until you're convinced it's either true or false. But I'm convinced this is true right at this stage. 20 minus 25 is negative 5. So that one's a solution. We do it all over again with x equals 1. Plug 1 back into the original equation. X equals 1, and we'll get 4 times the root of 1 minus 1 equals negative 5. Well, the square root of 1 is just 1, so this is the equation 4 minus 1 equals negative 5, but this is false. That means x equals 1 is an extraneous solution. It also means we have to do something on paper. If this was a quiz or exam problem to communicate x equals 1 is not part of the solution. For doing this as a homework problem in the Newton system, and we gave both solutions, we'd miss the whole question, which is really frustrating. So here's one way to communicate x equals 1 is definitely not a solution. A big angry X is a great way to say that. Everyone will take that to mean you've eliminated that from the solution set. Another way to say it is, I'll typically box out the answer. So the only answer to this equation is x equals 25. Well, we did it, folks. This one was trickier because one solution was indeed an extraneous one. It also turned into a review problem from chapter 6, solving the quadratic equation by factoring. We'll try out a few more in these notes just to see what else can happen in this section. And the next one is going to be a cube root for variety's sake. Any questions or comments so far? Okay, well, let's review why we took a square root on this one. The idea is we're canceling an exponent. The exponent's different on this one. It's really, if you take, say, the cube root of a, you're taking a to the power of 1/3. So that means squaring this equation is not going to be too helpful for us. If we raise both sides here to the power 2, we get a to the power 2/3. That's more complicated than what we started with. There's no reduction in complexity there. So here's what we would do instead. If it's a cube root of something, we raise that to a power 3. And the reason for that is a to power 1/3 raised to power 3 gives us a nice property with exponents. This is just a power 1/3. Multiplying the outer exponent, 3, this gives us a power 1, which is just a full cancellation. So we can eliminate the entire cube root by raising the outer power to a power 3. And that turns out to be the whole strategy with these next ones. If it's a cube root, we'll take this whole thing. It was the cube root of y. But now we raise that to power 3 for our cancellation. What we do to one side, we must do to the other. So let's raise this to negative, take this negative 5, raise it also to the power 3. At this stage, we're well on our way. There's a huge cancellation, cube root with power 3, leaves behind just y. And negative 5 cubed, that's 5 times 5 times 5, and it's going to come out as negative, so negative 125. At this stage, the whole problem is over, and some of the problems in the homework are really just this fast. We'll look at some more nastier versions of this where there's more algebra involved. But the thing that's really nice about this problem is the index three is odd. And so there is no extraneous solution. And the whole problem is over right at that step. So once you get the value, if you had an odd index, you don't have to do anything further. But that dash is weird. Let me take that off from right here. Well, we'll try out another one on part D. But part D is the dangerous one because the index is 4. It's an even index. Any questions so far at the moment? What makes this one really complicated in a certain sense is you actually don't have to do any algebra to this one. By visual inspection, this one is done. And here's the reminder of what's kind of similar to this. Way back, I believe in chapter 2, a long time ago, week 1 or week 2, we were solving absolute value equations. Let's see, that must have been section 2.7, part 1. Lots of weird things came up when we were doing these kinds of equations, similar to what we're looking into part D. We observed when we solve an absolute value equation, there's often 2 answers, but not always. If there's ever a negative right here, there's no solution whatsoever. And that's just because the absolute value equation, or absolute value itself, only returns a positive value. It came in, I think, a couple times. This one, when we added or subtract 6 from both sides, we had a negative 12 divided by 2, came out as a positive 6. So this one did have 2 answers. Let's see here. This one had 2 answers as well. I guess that's the only version where that came up as. So just this version where it was a negative value. So this was the one that was weird back in the day. It's the same concept over here. If the index is even, then the nth root of anything you put here, let's just call it a for anything, it could be a 6x minus 10, this is always greater than or equal to 0, kind of similar to absolute value in a certain sense. So the moment the problem starts with a negative 3, there's nothing we're going to be able to do algebraically to get a solution out from this. Even if we raise both sides to the power 4, algebraically we'll get a number, but that number when we plug it in is never going to check as true because you can never get a negative number out for any even root. So just for a quick example, the square root of a is always greater than or equal to 0. The 4th root of a is always greater than or equal to 0, and so on. The 6th root, the 8th root, and every even root whatsoever can never turn into a negative. But that means this is a fast problem once you spot it. You can just say here, no solution, since the index is even and the other side is negative. So that even index is that 4th root that we're looking into right there. So again, some of them are kind of nice. If it's something like this, all you do is raise to power 3. You don't even have to check your answers. If it's a 4th root or a square root and so on, but one side is negative, then there's nothing to do at all. It's much like looking into this one. Absolute value of 6x minus 10 equals a negative 7 would also have no solution. So let's try out a slightly different version, part E, to see how this one can go. I think we can solve this one in the required amount of space. And notice this one's just written in a kind of slightly different way. What we're dealing with is a cube root, but we have different versions or different ways we can write this. It's just a stylistic choice. Y plus 18 to the power of 1/3 is the cube root of y power 18. So that was our big punchline in our section 8.3 on radical expressions. So either way, this is a cube root. So that means we're dealing with an odd index. So there'd be no extraneous solutions to this one once we go to solve it. But by the way, this is a tricky one to solve. You don't want to raise this to power 3 because then you have to expand out y plus 18 to power 1/3 plus 5 cubed, and that could take us all day. Instead, we isolate the cube root expression. This one's very similar to what we did on this portion. You wouldn't want to square this in that format. That's a lot of work. Instead, isolate the square root term for root x. So here, let's start by subtracting 5 from both sides. We have y plus 18 to the power of 1/3 equals negative 2. And in view of the last problem, this seems concerning, but this one does have a solution. It's exactly 1. It cannot be an extraneous solution. And the only reason this one does have a true solution is because the index is odd this time. This one's to a power 1/4 or a 4th root. This one's to a power 1/3 or a cube root. There's no funny business with this one. There's no solution scenario like we saw here just because of the negative right-hand side. So this one solves nicely and cleanly by just cubing the left-hand side, raise it to power 3. Cubing the right-hand side, do the same thing on the right-hand side, raise that to power 3. We then get a cancellation here. Power 1/3 to the outer exponent of 3 just gives us y plus 18. Negative 2 to the power 3 is just a negative 8. Then subtract 18 from both sides, and we get y equals negative 26. Then the whole problem is overwrite exactly at that step. So sometimes these problems are pretty fast. Sometimes they take a little bit more work to get through, like on the next version we'll take a look into. But these are the major scenarios that we're going to be looking into when we do section 8.6 in the homework, solving the radical equations. So we have just one more before we finalize these notes. Any last questions or comments or thoughts to share so far? Okay, so here's our last one for the day, or not for the day, for the section's notes. Hang on, I lied, there's 2. So we have a bonus part G as well. Let's hide that for the moment, but not too much so I don't forget about it again. Looks like these are both square roots this time, so we have to be careful with extraneous solutions on both of these. This one's nice because the square root expression has been isolated, so we can start off by just squaring both sides right as it stands. So we have w plus 2 to the power of 2 is equal to the square root of 5w plus 6 to the power 2 as well. You don't have to write this in, but I just want to emphasize we're using that power 2 just because the square root has an index of 2. This gives us the cancellation on the right-hand side, just a 5w plus 6. And when we FOIL out the w plus 2 squared, you can expand it out as w plus 2 times w plus 2, but you can also think of it in these terms. This is just one of those expressions, a plus b squared, from our special factoring section in chapter 6. I think this was section 6.3. Every time you FOIL this out, you get a squared plus 2 times ab plus b squared. So a fast way to FOIL this out is take w times w for w squared. We'll take w times 2 for 2w, but you get 2 copies of that, so double it. So plus 4w plus 2 times 2 for a 4. So this is the equation we would solve. We now need to subtract 5w and 6 from both sides. Now it's a polynomial equation on the left. W squared minus w minus 2 equals 0. So we've come from a radical equation, which is pretty abstract, to something more concrete. It's now a quadratic equation, but still complicated because you can't isolate the variable w. These are unlike terms, unless you factor and use a zero product property. So this splits as w times w minus 2 and a plus 1, so it's a fast factorization. And then this implies w minus 2 is 0, or w plus 1 is 0. And we're looking at 2 possible solutions. W is either equal to 2 or negative 1. So these are candidates. It could be both are solutions, none of them are solutions, or exactly one or the other is a solution. So what we do is, now we check this out. Just as a reminder, the index 2 is even. So this means extraneous solutions are possible. So we check out both the solutions, starting with this one, w is 2. When w is a 2, we go back to the original equation and substitute. We have 2 plus 2 on the left-hand side. Then it's going to be root 5 times 2 plus 6 on the right-hand side. So now 4 equals the root of, this is 10 plus 6 for 16. And that looks great. The square root of 16 is a 4. So w equals 2 will check out. Now let's look into the negative 1. As a negative 1, plugging it in here, we have negative 1 plus 2 equals, plug in negative 1 right here, square root of 5 times negative 1 plus 6. On the left-hand side, this is now a positive 1, equals the square root of, this is negative 5 plus 6, which is a positive 1. And that works out as well. Square root of 1 is equal to 1. So negative 1 also solves this equation. So this is a situation where both solutions actually worked. This one had no extraneous solutions whatsoever. It's tricky to start because we have to make sure we're foiling out this part carefully. We're canceling the 5w plus 6. If we make any mistakes in the algebra, the factorization might be very, very difficult to get through. Maybe it requires the quadratic formula, or maybe there's no solutions to the factorization. So be really careful with the algebra in the middle, and then also double check the solutions, and then you'll be on your way with this one. Well, here's the last one for these sections notes. Let me double check. Yes, this is definitely the last one. It's also a pretty tricky one as well. It's another square root, so we want to square both sides. But if we square both sides in that particular format, the algebra just becomes monstrous. You'll have to FOIL this whole thing out. It's much like squaring out w plus 2. You don't just square the first term and the second term, you get 3 whole terms. And the thing in the middle is just going to be another square root if we square root or take this whole thing to a power 2. So the major idea is we want to try to isolate the roots. Well, that could be done in one step. Just add root 6y minus 2 to both sides. And the new equation is that the square root of 9y minus 14 equals the square root of 6y minus 2. In a real sense, they're both isolated on both sides of the equation. So let's square both sides. The square root of 9y minus 14 to power 2 is equal to the square root of 6y minus 2 to the power of 2. We're using power 2 because we expect the cancellation with the root and the outer power of 2. So now it's just 9y minus 14 equals 6y minus 2. So after squaring both sides, we freed up the variable y. Now we can say subtract 6y from both sides. 3 minus y minus 14 is negative 2. Add 14 to both sides. 3y is 12. Then divide by 3. Y is equal to 4. But just like on every other square root that came up, this isn't the full story. This could be the solution, or maybe there's no solutions to this. We have to plug it back into this original equation and see if it checks out. So let's do the check. Not W, but when y equals 4, we get over here, square root. 9 times 4 minus 14 minus the square root. And then another substitution here for y. 6 times 4 minus 2. This has to come out as a 0. So on this portion, it simplifies to, this is 36 minus 14. On this portion, we get 24 minus 2 equals 0. Let's take one more step. 36 minus 14 is going to give us 22. Minus 24 minus 2 gives us 22 again. But these are like roots. They're both square roots. The radicands are 22. So 1 root 22 minus root 22 does in fact give us a 0. That tells us y equals 4 does check out. And so this one has the unique solution, y equals 4. But we did it, folks. This is the full landscape of solving radical equations when square roots, cube roots, or otherwise show up. Well, any last questions at all before we take a look into that last short section? Okay, so here's the last concept for today. This looks kind of strange and kind of out of nowhere that we're taking a look into something called complex numbers or imaginary numbers. Reason for that is we're going to solve more polynomial equations in the next chapter 9, quadratic equations and so on. But something kind of strange comes up when we go to solve just about any quadratic equation. Sometimes the solutions we come up are not considered real numbers any longer, and we get what's called a complex number. So as a warm-up before we go into chapter 9, that's what the purpose of section 8.8 is all about, looking into the complex number system. So we have down below the so-called imaginary unit I and how it's defined. I is the square root of -1. And square roots of negative numbers did come up. That was in section 8.1. And notice what we said when that came up. Let's come down below here. When we had, say, the square root of -81, we never said undefined. That's because this class defines these quantities. What we said specifically is it's not a real number. We were looking ahead. The kind of number it is called a complex number instead. So that's the idea of what we're looking into in this section. And as a warm-up to all of these concepts, let's look into solving just 2 quick quadratic equations. X squared minus 1 equals 0 versus x squared plus 1 is 0. These solve pretty quickly. On the first one, you could either factor this as a difference of squares. That's the ordinary technique. But here's another strategy we're going to use in chapter 9. You could just isolate the power 2 quantity. It's kind of like isolating the square root. You get x squared equals 1. Then you could take the square roots of both sides of this equation. When you do that, you have square root of x squared equals either a positive or negative square root of 1. Here's the new thing that's a bit of a surprise. Taking a square root of both sides of the equation gives us 2 possibilities, a positive or a negative output. There is a cancellation on the left. Square root of x squared will give us just an x. And there's 2 potential solutions. Square root of 1 is just 1, but the 2 answers are either positive 1 or negative 1. So in other words, x equals -1 or positive 1. So this is kind of a new way to solve it. Just to connect up how we've done it before, another way to look into this is x squared minus 1 equals 0. Well, this factors, and if we were in, say, chapter 6, that's what we would do. We would factor it as a x plus 1 times a x minus 1. It's a difference of squares. Then we would set both factors equal to 0. X plus 1 is 0, or x minus 1 is 0. Solve both of them, but we get the same kind of values. X equals -1 or +1. So it's the same kind of output, the same solutions, just different sort of algebraic technique. But you know what goes awry on part B is the factoring technique doesn't work as expected. That's because we also mentioned when we were way back in, which section was this? Chapter 6 on factoring, the special products, that this one is kind of different. This one is considered to be a sum of squares. And whenever we had a sum of squares, here's what we said about that: not factorable. But we were specific, sort of. There's an additional comment. It's not factorable if you're using ordinary real numbers. So x squared plus 1 is much like the 9y squared plus 25. And x squared minus 1, the one that did factor, is much like, say, x squared minus 9. Factoring is x plus 3 times x minus 3. So factoring is kind of different from this one. But we can take this same sort of technique, simplify this by isolating the x squared portion. You get x squared equals -1. Square root both sides. So we'll have root x squared equals two possible answers, positive or negative, square root of -1. But that definitely looks odd. That's kind of like looking into square root of -81. If you try to come up with a real number to check this against, the check always fails, like when we discussed in this portion here. So square root of -1 is not a real number whatsoever, but it's a new kind of number. It forms a portion of the complex number system, and we're going to define the square root of -1 to be I, sometimes referred to as the imaginary unit. So we say to this one, the solutions to x squared plus 1 equals 0 are x equals -I or x equals +I. And this is some of the work that we're going to be looking into a lot more closer in our next chapter 9. It's going to lead us to things like the quadratic formula or completing the square, techniques that we haven't yet to really discuss or get into. But this is the warm-up topic on why we define I to be square root of -1. We want to solve all polynomial equations, even ones that can factor using real numbers. We want solutions to these as well. And the only way to make that happen is you have to define this brand new symbol. Because it's a weird thing, example 2 and example 3 is just focusing, working with this. Any questions at the moment before we try out example 2? Okay, example 2 is all about working with I. It's not a bad idea to just start this off by rewriting I equals square root of -1, kind of gets it in our brain to think about it, mull it over. Our goal is to evaluate I squared, I cubed, I4, I power 5. So next, if I is square root of -1, we want to compute I squared. Well, I squared algebraically is just taking this thing. We make a substitution and we raise to the power 2 the square root of -1. Just like in the last two sections, this power 2 nullifies or cancels off the square root. So square root of -1 times square root of -1 is defined to be, in this context, -1 itself. So if I is defined to be square root of -1, we define I squared to be -1 itself. So that's 1 down, 3 more to go. So if we can do I squared, we can also do I cubed, but we have to start using exponent laws. Here's the trick to make this happen. We break this down into something we know and just compute from there. I cubed can be factored as I, we know what that is, that's square root of -1, times I squared. So if we were to expand this out, this would be I times I squared on the row above became -1. And this just turns into negative I. It's kind of strange. And sure, you could put in negative square root of -1 here, but typically for these kinds of problems, the best way to write it is in terms of I itself. So that would be considered the most simplified form. I to power 3 comes out as negative I, and that's 2 down now. This is a kind of game that can go on forever, and what's amazing about it is these values start to repeat. This is a cyclical process. Let's look into I power 4. Well, I power 4 can be factored down into I squared times I squared. We know what I squared is each time it occurs. I squared is -1. So we made that substitution here. And now we can make the substitution twice in both of those spots. This is just equal to -1 times -1. But that means, very strangely as it seems, I to the power 4 is +1 out of nowhere. And this is where it starts to repeat. So that's 3 down. And now if we do I power 5, I to the power 5 becomes I times I to power 4. And we know what I power 4 is. That's just a literal 1. So there's a 1 just right in that position. This becomes I times 1. And we just get I right back. So I power 5 is just I. If we did I to the power of 6, we'd be getting -1. I to power 7 is negative I to power 8 is back to +1, and it just keeps on repeating in that same cycle. So that's another look into where does I come from? It comes from the goal of wanting to solve these kinds of equations. And example 2 is just working with I. The context that I is actually going to show up in chapter 9 is a little bit more similar to what we're going to see in example 3. In example 3, we want to simplify these things. These show up whenever we use the quadratic formula for certain kinds of quadratic polynomials. So if we can simplify this in a nice, clean way, that's the whole purpose of why we're working with I to begin with, just to simplify these kinds of square roots as we see them. So the concept is, we square root a negative number, b is positive, so negative b is now a negative number. The negative portion right here turns into I, and the whole thing just becomes I times the square root of b. So these go pretty fast. Negative square root of -7 becomes I square root of 7. The negative part right here becomes the complex unit I, and that's all we have to do for this problem. It's totally solved right at that step. Some of the fastest problems we've seen in a very long time. Definitely tricky and interesting on the way we're using I. Some of them go kind of fast. Others are a little bit trickier, like part C, so I'll spend more time with this one. But let's move into part B next. It's the same concept as before. There's a negative like you see here. This turns into I times the square root of 121. But this problem is a little bit more built up because it turns out 121, that is a perfect square. This is now I times 121 is just 11 times 11, or 11 squared. So we take the square root of 11 next, and we get I times 11. And that's totally correct as written, but the more standard way we would write this number is as 11I, keeping the complex unit to the right, kind of like a variable x in a certain sense. So square root of -121 is 11I, and we could do the same kind of thing with square root of -81. That would have just been 9I altogether. So they're not real numbers for certain, but we can now start simplifying certain expressions like these. Part C is a little bit more annoying because I don't know the square root of negative or of 180 itself. It looks like it's not a perfect square. So this is one where we probably want to start factoring it down. So let's take 180. We can divide by 2 because it's even, we get a 90. Divide by 2 again, and we get a 45. 3 will divide into this, going in 15 times. 3 goes in again, going in 5 times. And now we have a product of primes. 180 can be rewritten as 2 squared times 3 squared times 5. So there's several elements going on with this one. There's the negative sign, which is going to turn into the complex unit I, but also 180 simplifies as a root. So let's be a little more careful with this one and rewrite it as negative 2 squared times 3 squared times 5. The 5 here is going to stay trapped in the square root. Negative comes out as the complex unit I, and because we're taking a square root, we'll divide the powers here for base 2 and base 3 by 2 itself. So this turns into, first it's I coming from the negative sign times 2 times 3, or just a 6. 5 stays behind as the irrational parts. We can't simplify down any further. 2 by 6 makes up the 12, and just like I times 11 is better written as 11I, more standard form, we'll rewrite this as 12 times I square root 5. So square root of negative 180, and again, this is something that can come up in chapter 9, simplifies down to 12I root 5. And that's the end of the notes. Even though the notes are pretty short, it's a pretty wild adventure, but we'll be looking into complex numbers more and more as we go through chapter 9, starting next class. But looks like we're ending just a couple minutes earlier today. Any last questions or comments before we call it a night? Oh, thanks for mentioning that. That's one thing I missed on that one. And that's one thing that gets really tricky about these sections. So just for the sake of the recording, the answer for the one we looked into first should have had an absolute value at the start. And that's the difference between section, say, 8.3 and section 8.3, or excuse me, section 8.2 versus the 8.1. And section 8.2, we made this big, huge assumption. Assume all variables represent positive real numbers. And when that assumption goes in these sections, it means we wouldn't be using absolute values. But in other problems, like in section 8.1, for example, without that assumption, whenever there's an even index, that's where the absolute value would come in to play, like you're mentioning on that problem. So thanks for mentioning that. These are pretty tricky questions because without the full instructions written in, it's hard to know exactly what they're going for. Does that make sense on the differences between those two different kinds of answers? Yeah, absolutely. And thanks for mentioning that other additional issue. That's really technical as well. I think this will help out a lot of people when they go to watch the video. And for next class, if anything weird comes up again in these sections, any problems that just don't seem to be working out to right, feel free to bring them to start out in class as well. I'll be happy to help with those. But have a great night. We'll be back to chapter 9 next time on Thursday. Take care.